If we look at this pretest that you just took, it gives us a way of measuring the friction force. Okay? Remember, everything's moving at constant velocity. Okay? If we're asked on that last question to compare the horizontal forces on the crate, well, let's get rid of the rock for now. We'll bring it back on Friday. But for now, let's get rid of it. If I draw the horizontal forces on the crate, I'm pushing on the crate, and the friction force is impeding the motion. And I put the force by me as greater because it's moving to the right. I'll wait. Is no one offended? Okay, someone's offended back there. Call me a liar. They have to be, okay, you wanted to say that all day. They have to be equal. Doesn't this one have to be a little bit bigger? No, they have to be exactly the same. If the acceleration is 0, the free body diagram has to scream 0.
So it doesn't matter if I put the N, instead of N, I listed it as F person?
This one here,
Does it have to say N or F? Or does
we're going to have all our forces labeled as one of our 5 flavors. Either weight, magnetic, normal, friction, or tension. We're never going to have a general F. Okay? Now, this gives me a way of measuring the friction force. If I think of the friction as all these nooks and crannies grabbing each other, that would be very hard to measure. It happens over the whole surface. But I can indirectly measure that by just putting a bathroom scale between my hands and the crate. As I'm pushing, I can just look at the bathroom scale and see how hard I'm pushing. If I'm pushing at constant velocity, the friction force has to be equal to my push. So I'm also measuring with the bathroom scale the friction. Now we're going to do a little experiment. And I have 3 volunteers. Thanks for volunteering. Come on up. I have a sled here. Your name, sir?
Brandon.
Brandon?
Noah.
Noah?
Jenny.
Jenny?
Yes.
Jenny, I want you to get on that sled, and gentlemen, I want you to hold on to her arms so she doesn't fall off and sue the university, okay? It's your job to make sure that we don't lose money on this. Now, I'm going to pull Jenny across the... I'm sorry, is Jenny? I got it right at my age. I'm going to pull her across at constant velocity. Now, clearly, I have to speed her up to get to constant velocity. I don't want you to see that. So everyone close your eyes. Not you two, gentlemen. You keep your eyes open. Everyone else, close your eyes. I'll tell you when to open them. Okay, now you can open them. She's going at constant velocity, and the reading on the scale is about 180 newtons. Okay? Good job, guys. Good job. Okay, come on back. You're not done. Okay, Noah, get on there. The other, keep him safe. Everyone close your eyes until I get them up to speed. Oh my goodness. No, Brandon, you get on there. Switch. Sorry. Okay, hold on. Okay, close your eyes. Brandon, it's just like surfing. Get on there.
I don't see.
Stay on there. Okay, keep him on there. Okay, now you can look. He's going at constant velocity, and it's like 370. That's all I can do. Let's give him a hand. Now, if we had the time and the energy to do this over and over again, we would find that all of our data points lie on a straight line. That as we increase the normal force between the sled and the floor by putting larger and larger people on there, we increase the tension force in the cable. Now, that tension force is an indirect measurement of the friction if the sled is moving at constant velocity. The friction has to equal the pull by the tension. Now, whenever I have a straight line graph like that, oh, first of all, what if instead of going at the speed I did, the slow speed, I had you close your eyes longer and got them up to a much faster speed. So they were just zipping across this room. What would happen to my graph? Yeah, you have no way of knowing, but if we had done it, nothing at all would happen to the graph. That's another gift from nature. It does not depend on how fast you're going. Now people, everything I'm saying today does not apply to the wheels on a drag car racer. They spin those wheels so fast that they get hot, they get rubber, the rubber starts to melt, they change state. Okay? We're not talking about that. We're talking about regular surfaces going at regular speeds that you'd encounter in everyday life. Okay? Now, if I have a straight line graph, your math class suggests that the equation for it is y is equal to mx plus b. This is the slope. This is the y-axis, the x-axis. This is the y-intercept. That line goes through 0. The y-axis is the friction. The x-axis is the normal force. And this slope, instead of an m, we give the Greek letter m a mu. And it's called the coefficient of kinetic friction. Now, let's see what that means. If I were to cover the bottom of that sled with sandpaper and do this over again with the same 3 people, would my graph look like this or that? Would it go higher or lower? Well, if this is the normal force with Jenny on there, and this is the normal force with Noah on there, with friction on the bottom of the sled, I'd have a bigger friction force. I'm sorry, with sandpaper on the bottom of the sled, I'd have a bigger friction force. So this one is a small coefficient of kinetic friction, a small slope, and that's smooth surfaces. This one has a large slope, a large coefficient of kinetic friction, and that's the rough surface with the sandpaper. So that gives me a feeling of what this coefficient is. It's a measure of how rough the 2 surfaces are, how much the nooks and crannies are grabbing on each other. Now we use the symbol mu sub k to indicate it's for the kinetic friction. That suggests that we're going to encounter a mu sub s on Friday. It represents the roughness of the surfaces. It turns out there is no supercomputer on the planet that is powerful enough to calculate one of these coefficients. Every single mu has to be measured by some poor engineer that actually does a measurement between hockey puck and ice, and now I'm going to do sandpaper and wood, now I'm going to do a different kind of sandpaper and wood. It's got to be the most boring job in the world. Now, this coefficient is just a pure number. If I look at the equation for this friction force, kinetic friction is equal to mu sub k times the normal force. Now the friction is measured in newtons, and the normal force is measured in newtons. And that means if this equal sign is going to be valid, this coefficient is a pure number with no units. And it's a number that is greater than or equal to 0 and less than or equal to what? Actually, infinity. It's a common misconception that it has to be less than 1. If you have super glue, you can make that mu as big as you want. Yes, you can. Okay? It can be very, very big. Now, the other thing I want to point out is that in a really good free body diagram, there's at least 3 normal forces. That's the most common type of force. And so if you're looking for the friction force between the floor and the block, you better use the normal force that has the same indices. floor, and block. That's another advantage of our labeling system.